Okay, let's get started on chapter 10, mechanisms and modes of mass transfer. This one mirrors chapter 2. You remember chapter 2 in heat transfer, we talked about conduction and convection. So just like that, here we will talk about diffusion and we will also talk about convection here. So then we are in this chapter here. So we are going to follow just like in chapter 2, diffusion and diffusion-like processes and then convection. Before these two, however, I want to cover something that is today's lecture, and it's not directly any of these modes, diffusion or diffusion with flow, but the flow itself, and in this case, flow through a porous medium. So this is what you would learn in a fluid mechanics class, except that flow through a porous medium is typically not included in an undergraduate fluid mechanics class. So I am going to talk about flow before we get to these two. So just remember that this part is only about flow. That will later be part of this convective mass transfer. But for now, it's just the flow. Now, porous media is basically everywhere. Porous media can be tissue, it can be bone, like you see here, bone as porous media. It can be wood, for example. And this is a micrograph of wood. So you can see the pores, and these are like channels. And so fluid can flow through these channels. And another example that we see everywhere is soil as a porous media. Now back to this picture on wood, this flow that you can see through that can happen through these individual channels, you can certainly use the Newton's law of viscosity and flow through pipe, the formula that you know, flow through pipes. You can certainly use that through one of these. It's still not going to be easy because these pores are not like straight through, they're tortuous, and they are not going to be circular and so on. But imagine, if this is a micrograph, means very small scale, so there are thousands and thousands of these kinds of channels. So yes, you can use the pipe flow equations, but it's going to be pretty much impossible to do any real problem like you would quickly want to know, let's say, flow through wood, for example, because each one is so varied and we don't even know how many of them are there. So this normal equation of flow through pipes is going to have trouble with porous media with so many different types of pores and so on. So we're going to talk about something that applies on the average on these kinds of pores. So it will give me an equation that is valid over the entire region. Here is another example of porous material. So in this case, it's rice grain. This is related to a joint project that we did with Unilever Foods from Holland. This is the structure, this is the porous structure that they got through different scanning procedure. So now back to what we're talking about. The average velocity through the pores is higher than through the medium. What do we mean by that? So think of this as a porous medium, and it has these different tubes, and so when fluid is flowing, fluid is not flowing through the solid part. It's only flowing through the openings, obviously. So if we think of a volumetric flux of fluid, normally it's kind of hard to know, keep track where there is a hole and where there's not a hole. So when you talk about flux, the meter cube that is flowing per meter square per second. So this meter square, we think of the entire area, meter square. This is my meter square. So when we think of how many meter cubes are flowing per unit area, per unit time, that's what is called the volumetric flux. So flux is always something per unit area, per unit time. Volumetric flux is volume flow per unit area, per unit time. But interesting part is this meter cube and meter square, they cancel, and we're left with just meters per second, which is like a velocity. So we can think of this volumetric flux is also like a superficial velocity. It's the velocity that the fluid is flowing with over the entire section, not just through the holes. In reality, it's flowing through the holes. So then, in reality, the actual fluid, the average velocity of the fluid, the real velocity of the fluid would be this superficial velocity divided by the fraction of pore area, which means the average velocity would always be higher. By the way, the fraction of the pore area, you can approximately think of that as pore volume divided by total volume. Even though we're talking pore area over total area, and as an example, if the tubes are all straight, then it'll be the same fraction. Pore area over total area would be same as pore volume over total volume. So that's kind of like the porosity. So this is the porosity. So we divide the superficial velocity by porosity to get the actual velocity through the pores. We're not going to do anything with this actual velocity, but you get the idea that the velocity of actual fluid flowing through the pores, they are not same as the superficial velocity. These are higher. Okay. So flow through a porous medium is given by Darcy's law. So yet another law. But you will see it is not fundamentally, sort of a different law as the ones that we have already talked about. So Darcy's law says the volumetric flux, which is meter cube per meter square per second, is proportional to the driving force. The driving force is the hydraulic potential. Hydraulic potential, this thing, you remember how you write P pressure equal to rho g h? It's the head. That's what is in here. So it's you can think of this as like gradient in pressure, except pressure is written in terms of a head. So flow is proportional to the driving force, and the proportionality constant, of course, is going to depend on what it's flowing through and what is flowing through. So this proportionality constant is called the hydraulic conductivity. So once again, to see similarities, Fourier's law talks about heat flow. So just like here you have volumetric flow per unit area per unit time, so here you have joules per meter square per unit time. um, heat flux. Heat flux is proportional to temperature gradient. So here this is the driving force, whereas here the hydraulic potential is the driving force. So it's the gradient in temperature that drives heat flow. It's the gradient in pressure, in this case the hydraulic potential, that drives the volumetric flow. And we will see later on, we will do Fick's law, some of you already know. That is also says the mass amount, so kilograms per meter square per second, is proportional to the concentration gradient. So this concentration is the driving force. So in the last slide, we talked about this flow that is proportional to the hydraulic potential. So what makes up hydraulic potential? So let's see some of the different forces that make up hydraulic potential. So first, this is a very common sponge that we would have in our kitchen or in the bathroom. This one hasn't been used, when it's completely soaked, as I take it out, you notice water drips out by itself. It doesn't need anything. That's because gravity is acting on it, and gravity is all that is needed for water to be coming out of the sponge. Now this process will stop. It will not stop when all the water drains out. It will stop at a point where the force of gravity is just equal to the attractive forces that there is, which I'm going to talk about in a second. So this was my gravity. As you can see, it is starting to stop dripping. And now we can have applied pressure. What is applied pressure? So we got more water in the sponge. And so if I have a column of water on it, that will push water through the holes of the sponge, and that will cause a flow of water through this porous media. Another one is we could have like a air pressure. Just air pushes out the water through this. So it can be hydrostatic pressure or it can be pneumatic, but it can also be this squeezing, so mechanical pressure. So mechanical pressure can squeeze the water out, meaning mechanical pressures can cause, the squeezing pressure can also cause flow through this. So all of these are kind of positive pressures. Now see what happens if I bring in a very dry sponge and I'm going to touch it to the water. And so before, water was coming out of the sponge, but now as you can see, water is coming up. It's not coming out, it's coming in. It's actually, water is getting attracted. So there's attraction between the sponge molecules and water, and it's pulling water into the sponge. So if we think of the last two, the gravity and the mechanical forces pushing water out as being positive forces, then this one, the water is experiencing a negative force. It's actually just being pulled into the sponge. And so then this one is because of the attractive forces, and capillarity is one of the attractive forces. So this one is a negative force that's causing flow of water into the sponge. And finally, I just want you to see that here is a sponge, and then you can see, for example, all the different
shapes and sizes of pores. So if you want to, for example, use your laws of fluid mechanics that says how much would flow through each pore of a different size. You can do that, but you can see how it will be hopeless because there are so many pores, that's one, different sizes, and then they're tortuous of, of different nature. They're not going to be straight pores going from top to the bottom. So size, how many of them, and the tortuosity, they're all different. So trying to use the normal laws of fluid flow through a pipe to this sponge is going to be hopeless. So we need to come up with some average formula that gives how much stuff flows through this porous media.
To summarize then from those experiments, hydraulic potential is made of, you can think of, it's made up of three things. Gravity as is a driving force that can push fluid through a porous media, and then applied pressure, like we talked about hydrostatic, pneumatic, and then mechanical, where I was squeezing the sponge. So this is a mechanical force. So both of these are positive forces where on the water to make water flow through the porous media. The matric force is due to things like capillary binding, and that's the one we saw where water was going up uh, against the gravity. It's going in the opposite direction. Of course, it's not helped by gravity. So these are negative or attractive forces. So these forces, these apply. So the metric force due to like capillary binding, due to addition to surface, due to osmotic bonding, they are applying a negative force. They are attracting and keeping the water in the matrix. These are the reasons that, let's say, water in our tissue, there's lots of it, it doesn't drain out because the water is attracted to the tissue matrix by forces such as these. So now we are going to use this as the entire hydraulic head or hydraulic potential. As I said, this H is just like pressure, rho GH. So this is the H that we are talking about here. So we are going to now interpret that hydraulic conductivity K that you saw in Darcy's law. We want to interpret that. We want to give some physical interpretation, and this is how we will go by. So for a moment then, let's think of an ideal porous media. So that looks like this. So you have a pore, another pore, maybe different size pores, but they're straight through. So in each pore, I can use the equation for pipe flow. So these are the pores. In between is the solid matrix. So this is the solid matrix. And so so remember the flow through a pipe, I can write Q, the amount of fluid that flows because of a delta P pressure gradient. The relationship between Q and delta P is given by this, where you have D as the diameter of the pore. Okay, so this is for one pore. Now let's write that for the ith pore. So let's see what we mean by ith pore. So in a porous media, there's going to be different size pores. Okay, small and large. And so let's say we pick some radius Ri, some radius, and so for that radius, so let's say I pick this one, for that radius, then the amount that will flow through that particular channel, that particular pore, is given by this, which is the same equation just rewritten. Okay, and then I have changed from pressure to H, because remember the final equation was in terms of H, and we always use this P equal to rho g H. Okay, so if this is through one pore of size Ri, then the total amount of flow would be what? Flow through each pore times however many pores are there of that size. So Ni is the number of pores of radius Ri. So Qi is through one pore, Ni/Qi is through all the pores of that size, and then you add it up over all different sizes. So it's added up over I. This is the total volumetric flow. So flux would be divided by area. So if I now plug in for Q, I simply get this expression. So all I did is I just plugged it in. So you can see Ni Ri raised to the power 4 over area del H del S. Del H del S is still there. The del rho G, the rho G I mean is here. Okay. So continuing, I want to rearrange that one, and basically we are done. So I just rearrange that same expression from previous slide to group things. So you see rho is density of fluid, mu is viscosity of fluid. So some terms in that in the expression relate to only fluid, so I group them together. Then some other terms relate to the matrix. How? Because I can write the term pi Ni Ri raised to the 4 as Ri square times Ri square. And then what is the meaning? Pi times Ri square is the area of one pore, and Ni is the number of pores of that same size. So this is like the fraction of pore area that has Ri. Now that divided by total area is the area fraction of pores of radius Ri. Now area fraction approximately can be taken, especially if we have straight tubes, then the area fraction is same as volume fraction of pores. So then so that multiplies, this part of it is then volume fraction of pores of this size Ri. So these are the size of pores and what volume fraction is occupied by pores of that size. So this has to do with the matrix. So all of this entire thing has to do with matrix. So this is fluid part, this is matrix part, and then multiplied by the gradient. So if I rewrite that, I call this whole thing as K. So K, all the matrix related factors are together called the permeability. This is called the intrinsic permeability, and then intrinsic permeability has the unit of meter square, because see this part has no unit, so it's only Ri square. So this has a unit of meter square, and this is only a matrix factor, whereas the rest of it is fluid. Okay, but together then this is actually what we had, hydraulic conductivity, because the equation now can be written as this. So K is just made up of these two guys. Okay, so my Darcy's law, this is my Darcy's law. This is what I had said few slides ago as the Darcy's law. So then I can come to Darcy's law by considering the porous media as bundle of tubes, and then I can give some interpretation of K. So you notice, by the way, that the equations that you had for flow through tubes, those didn't get thrown. We can start from there and then actually come to Darcy's law. And this allows me to interpret K in terms of the different parameters. The matrix parameter, K permeability, and density, viscosity, which are the fluid parameters. Now, of course, real porous media I would not be able to derive like this. So in general, then, we use this equation, but the interpretation of K stays the same, that K carries with it the fluid property and the matrix property. So in a live classroom, of course, we will have questioning, but here are the two questions that I want you to think about. Transport of a fluid through a porous medium, is it faster for oil or water? And you think of why, and you think of use Darcy's law just derived. So it has the K, it has the rho, it has the mu. So you use the formula that we just derived to answer why or how the formula actually predicts how oil would behave through a porous media versus water. Likewise, if you have pores that are on an average larger pore size, basically amounting to higher porosity, larger pore size, why would fluid flow through it faster or slower? I need you to check for yourself using the same formula that we just derived, thinking of the flow through porous media or the porous media as bundle of tubes. So here are some representative values for the intrinsic permeability. That's the K part, the small k. The intrinsic permeability, and you can see gravel, those things are very porous, so it has the highest intrinsic permeability, and then it drops as you go this way to sand. And things of interest for us is, for example, intrinsic permeability through meat. Now you would wonder, why in the world would I care for intrinsic permeability of fluid through meat? So we actually in this class, not in this class, but the other class that I teach, we had worked on design of a auto syringe. So how much pressure is needed to push a fluid automatically through tissue? And guess what? Then pushing fluid through tissue, you need the permeability. And so I actually personally measured these meat permeability for some other application. It was for how water moves inside meat during cooking. But the same intrinsic permeability values were useful in the context of design of an auto syringe, where the syringe will push some liquid into the tissue. So then the biomaterial, the tissue, were somewhere here in terms of intrinsic permeability. So for convenience, I want to divide flow through porous media into two situations, and we'll see why. For saturated flow, we just use the Darcy's law with the hydraulic conductivity, what we just talked about, just discussed. When it's unsaturated, what is an example of unsaturated? Remember in the experiment I showed that with a very dry sponge, unsaturated means, whereas saturated means all pores filled with water. As soon as you drain out some of the water, then it becomes unsaturated. An extreme situation for unsaturated is the example that I showed of the sponge, the dry sponge, for example. So it's a dry biomaterial, for example, would behave this way. So what did the dry sponge do? It was soaking up water, it was pulling water through it. So unsaturated, we will see that under those conditions, this Darcy's law can be written like Fick's law, which we have not done yet, which is for diffusion. So let's skip any more details of Fick's law, and we'll see how we can write it. In unsaturated flow in a porous medium, we saw that matric potential drives the flow. How did we see that? You remember how water was pulled into the sponge when it was a very dry sponge against the gravity. So it is the matric potential, the attraction between the molecules of the pore matrix and the water that was pulling things up. And so for a simple capillary tube of radius r, you probably recall from physics that the capillary height of capillary rise is given by h equal to this expression, where gamma is the surface tension of the fluid and r is the radius. So the capillarity pulls things up against the gravity, and that's what we saw in the sponge, the dry sponge that was pulling things up. So just to be sure, then, what are the kind of forces that are active? So in general, the head that drives the flow can be made up of gravity, g, in this case written as z height, and then h as all the other forces. What forces? You can have applied pressure, like squeezing, or you can have some other hydrostatic pneumatic pressure. But in absence of those, then H is only made up of the matric potential. So this is the negative matric potential. So for unsaturated flow, it is only the negative matric potential that drives the flow. So it is the difference in the interfacial tension that drives the flow in unsaturated. So what you want to remember is that it is the matric potential, the attraction to the solid matrix, that is the most important. Gravity can be ignored, and depending on the situation, other pressures can also be ignored. So now I want you to see that in case of the special case of unsaturated flow, where only this H is important, as I showed in the previous slide, gravity is not important, and there are no other applied forces, then for unsaturated flow, I can actually show that this is analogous to diffusion. I understand we have not talked about diffusion, but just go through the process here, see, you may even relate it to diffusion that you have seen in other courses for now. So the volumetric flux by Darcy's law is JV equal to minus K del H del S, and if I change from volumetric to mass, all we have to do is multiply by the density, and I can rewrite this. So this is gradient in head. So del H del S. I can write that as del H del C. C is the concentration of water. So remember how the sponge was pulling up water. So there's more water here, less water here. So the concentration of water here versus here, that's what we're talking about. So how does the concentration change with position? This is my position variable S, the distance. That's the interpretation of this term, and this term is how the attraction varies with concentration. So you notice that you can almost think of this piece of sponge as something hungry. So up here, when it's hungry or thirsty would be the more appropriate one. So here it's more thirsty because it does not have enough water, because this is dry. So it does not have enough water, so it's more thirsty. So it has more attraction for the water. Whereas down here, it is not as thirsty. Its thirst has been quenched by water, so it doesn't pull the water as much. So the pull is what we mean by H. So the pull varies with position from here to here. So this del H del C is how the pull for the matrix is felt by the water, and how that varies with amount of water. So if there's more water, like here, the pull is much less. When there's less water, the pull is much more. So it has to do with the property of that material. How much does it attract water? We will talk about that in a second. But right now, you can see all of this quantity can be lumped into something. Let's say for now we call it D, which we really mean diffusivity. Later on, I will show that this is the form of Fick's law. The mass flux is proportional to concentration gradient, so del C del S, and the proportionality constant is D. So in here, D is capillary diffusivity, okay? And this capillary diffusivity is made up of these terms. So let's look at these terms, how they vary in a real material. So in a real material, in this case it's soil, the head varies this way. So lower the moisture, the higher is the attraction. And you can see higher, but it's a negative value. It's higher is the attraction. So less water the biomaterial has, more tightly the water is held to the matrix. So harder is for the water to be removed. And this K also, K is the hydraulic conductivity. Now as you remove water, it is the bigger pores that gets emptied first. So now water is in smaller and smaller pores. And in the smaller pores, the water is held more tightly, so the K or the K has to do with the transport of water. And now we're talking about water in the smaller pores. So in smaller pores, K has to be small because things cannot move as easily. It's in small pores. So K drops with moisture content. And I have already said that H changes this way. Together, we see the typical capillary diffusivity of a material. So this is typical. This one is for soil. but for other biomaterials and so on, the trend stays the same, which is the diffusivity, the capillary diffusivity drops with moisture content. And you can remember it this way, that as the moisture content goes down, water is held more tightly by the matrix, so it cannot diffuse as easily. Also, the water can only flow through smaller pores, so that also makes the water to move, uh, that also makes it harder for the water to move. So the capillary diffusivity drops. What I want you to remember is only this part, that the capillary diffusivity in a biomaterial, in any porous material, drops with the moisture content.